All right, so let's talk about the electric potential, and we're going to try and do a couple things after last night's class. So one is I'm going to break this up into smaller chunks. So instead of sort of throwing all of this at you in one fell swoop, we're going to break it up into three smaller videos. Hopefully, I'll also be able to deliver this a little more slowly than what I did in class last night, so that should also help. But the other thing that we're going to do, because one of the key questions that seemed to still be frustrating a lot of students at the end of class yesterday was there seemed to be sort of this attitude of, okay, great, I can calculate the electric potential due to point charges, but I still don't have any idea what that actually is, what it means, what it's trying to tell me. So let's see if we can sort of start again and kind of set this up a little bit better, so maybe you've got a better feel for what the electric potential is trying to describe. So to do that, let's actually start by thinking about the gravitational field. And again, let's think about the gravitational field we know best. Let's think about the gravitational field near the Earth's surface. So here's the ground. Here's the gravitational field near the Earth's surface. It points down. It has a magnitude of g equals 9.8 meters per second squared. And all I'm going to do is I'm going to take some object, and I'm going to start with it at some initial height, and then I'm going to move it upwards to some final height. And I know that in order to do that, I have to do work. And the work I do has got to be related to the change in the gravitational potential energy of the object. So again, we can calculate this, right? We got very comfortable calculating this in 221. And I know that I calculate the change in the gravitational potential energy of my object. In this case, it's going to be a plus because I moved it away from the surface of the Earth. It depends on the mass of the object, the Earth's gravitational field, and what height I chose to move it upwards. So when we look at this expression, this is the gravitational potential energy, but we can break this up into two pieces. The mass on one hand, the mass of the object on one hand, and everything else on the other. And why this is useful and where this is heading towards talking about the potential is that the mass is telling us something about the object being lifted. Everything else is really telling us something about the field the object is being lifted in and how you're choosing to move your object within that field. So what's going on here is that the change in the gravitational potential is trying to tell you just about this. So it says, I want to tell you how much work per mass you need to do to move a massive object around in a gravitational field. And so that depends on two things. One of them is it depends on the field itself, right? So what's the magnitude and direction of the gravitational field you're choosing to move around in? It also depends on the points the object moves between. So initially the object was here, at the end the object was there. So this would be the change in gravitational potential. And again, you can see that it depends on the strength of the gravitational field, that's G. The H is telling us how far we moved, and then the plus is telling us how we moved relative to the direction of the gravitational field. So the gravitational potential is trying to tell us really about how you're moving around in the Earth's gravitational field. So we think of that as the work per mass, because basically we're saying I'm getting rid of this piece. So my work is here, but I'm getting rid of that mass term because I don't care. I don't want it to matter whether I'm moving some small light object or some large heavy object. I just want to depend on my location within the field and how that's changing. So with that in mind, let's think about an electric field. So here I have a positively charged plate, a negatively charged plate. I've got an electric field that points to the right. And again, let's say that I want to think about moving charge from this initial position to this final position. So that's going to require work to move that charge around. The work I do is going to be related to the change in the electric potential energy. So, but I know the electric potential energy is also going to depend on the charge that's moved, right? So if I have a positive charge that I put here at my initial position, well, clearly it wants to move towards the negative plate. So it wants to move this way, which means I would actually have to do negative work to keep it from running away. On the other hand, if I've got a negative charge that I start with here, well, I know that it actually wants to move to the left. It wants to move towards that positive plate. So I would increase the potential energy of a negative charge by moving it from this initial position to this final position. So for a positive charge, the potential energy would decrease in following this path. For a negative charge, it would increase in following this path. So again, the change in the potential energy depends on the charge. And all we're trying to say with the electric potential is that I don't want that charge to matter. So the change in the electric potential is telling me how much work per charge I need to do to move a charged object around an electric field. So again, it's telling me about just the field and how I'm choosing to move around that field. Again, notice that depends on the field itself, what's its magnitude, what's its direction, and then the points we're choosing to move between. So how did you move relative to that particular field vector? So this is hopefully conceptually that's giving you guys a better sense of how we're going to build this idea of the electric potential. It says I don't want to care about the charge I'm moving around. I just want to think about how as I move around in space in a particular electric field, the work that I do per charge changes, how that changes. All right, so now let's come back to sort of the way we set this up last night. And we said, well, what we did with the electric field was we said, well, there's this quantity called the electric force, and the electric force depends on both a source charge and a test charge. It depends on two charges. If I get rid of the impact of the test charge, then I'm left with the electric field that only depends on the source charge. So just to be clear about what we're sort of defining these things as, the source charge is another way of saying the charge that's creating the electric field, and the test charge is the charge that I'm placing into that electric field. So the electric force depends on two charges, both source and test. The electric field just depends on one. We play the same kind of game when we're talking about the electric potential and how it relates to the electric potential energy. So again, the electric potential energy depends on both a source charge and a test charge. The change in the electric potential, or the potential difference, I'm dividing out the impact of that test charge, so it only depends on the charge that's creating the field. And then how I move around within that field will tell me about how the potential is changing. So for units, again, if I think about that previous equation, the units for electric potential are going to be equal to the units of electric potential energy divided by units of charge. So I know that's going to be joules per coulomb. This also gets called a volt. So from a naming perspective, because this is something that causes a lot of confusion for students, so let's make this as clear as we can. There are multiple ways that I can talk about the electric potential, and they all mean the same thing, and they all have voltage, they all have volts as their unit. So I can talk about the electric potential difference. That's literally just sort of reading this off, or the change in electric potential. Those two things mean the same thing. Once I pick a 0 point, I can also talk about the electric potential. And I can talk about the voltage, again, just sort of turning this unit into another way to talk about electric potential. So all four of these things get used interchangeably. They all mean the same thing. What is something that is clearly different is the electrical potential energy. So as soon as you tack energy on the end, that's a different thing. So the change in the electric potential energy, that's our delta U. The change in the electric potential, that's our delta V. Those two things have different units. One has units of volts, one has units of joules. But there are a lot of ways that we will end up referring to electric potential, so just keep that in mind.